All right, kids. So some things that we're going to start dealing with today is this. We're still going to continue with this idea of right triangles here, all right? So if we're dealing with right triangles, is Pythagorean Theorem still something that we can use? Yeah. Absolutely. So don't lose sight of this, all right? Don't lose sight of the fact that we're still going to be able to use a squared plus b squared equals c squared, okay? And this would apply to any right triangle, but our job today is to not look at all right triangles, but look at what types of triangles. Okay, there's two special right triangles that we're going to talk about today. And that question is going to address them. It says right here, what is the relationship among the side lengths of, all right, here's the first one, kids. 45, 45, 90 triangles. You know, what's the other one say, kids? 30, 60, 90 triangles. And they want to know what's the relationship between those two types of triangles. So one triangle that's going to be special to you is a 45, 45, 90. The other one that's going to be special is a what? 30, 60, 90. What number shows up in each of those? 180. And they're all going to add up to 180, but what number shows up in these trio of values? 90, meaning they are what type of triangles? They have to be a right triangle, okay? So we'll show you how we get those here in a second, but the question is going to be, what are the relationships of the side lengths there? So the first thing we're going to start looking at, guys, is this. We're going to look at finding side lengths in special right triangles, and we're going to look at some real-life problems involving special right triangles, okay? Now,
Whoa.
what did I miss? Mikhail, fill me in.
I'm just know how to be quiet. That was the funniest reaction ever.
Okay, here we go. Come on, guys, focus. Okay. Isosceles triangle. All right, this is going to show up a lot today. But an isosceles triangle says in geometry, an isosceles triangle is a triangle that has what?
Two sides.
Okay, it could be, if you have three sides of equal length, you have two sides of equal length. You do, don't you? Okay. So keep in mind here, I agree that an isosceles triangle has two equal lengths right here, okay? But what I would tell you is this. Focus on the idea that if you have at least two sides equal, it can be an isosceles triangle. What do you call a triangle with three equal sides? Remember? Equilateral. Equilateral is going to come up as one of those triangles that would still have two equal sides, although how many sides are equal? Three. So we're going to kind of focus on two equal sides here today. Let me just draw this real quickly. You want to draw something like this. So in geometry right here, if I have an isosceles triangle like that, at least how many sides have to be equal? If I put a little tick mark here and a tick mark here, what's that mean? So those two sides are equal. So it'd be isosceles. You know that. Okay. All right, so let's talk right here. The first special triangle we're going to kind of talk about is called a 45, 45, 90 triangle. And there's a theorem for this right here. All right. First of all, anybody know where a 45, 45, 90 triangle comes from?
God.
Yes. Everything comes from that, right? Well, here's the deal. First of all, go ahead. Start out by drawing a, what shape have I got here? Pretty much square. Okay? All right. If I start with the square, kids. Okay, what's true about all four sides of the square? They're all equal. They're equal. Okay, and then furthermore, what's true about all interior angles of the square? They're going to be equal, and what is that value? 90 degrees. Okay, so here's the deal. If I know a square says all these angles are 90 degrees, and all sides are equal right here, then where does a 45, 45, 90 triangle come from? How? You would take and split this in half diagonally, kids. We would have, ooh, check this out, kids. 45, 45, 90 triangle is simply half of a what? It's half of a okay. And the idea then is this. I would say that down here would be a 90-degree angle, right here like so. Okay. What has to be true about the two legs then in this bottom triangle? It's half of a square. Well, what did you tell me about the sides of the square in the first place? They're equal. So this side on the left has to be the same as this side on the right, doesn't it? Or on the bottom, I should say. So here's my question, kids. If this diagonal cut these 90-degree angles like this, probably cut them in half, didn't it?
Yeah.
What is half of 90?
45.
Which means this angle right in here would be how many degrees? And this angle right in here would be what? So guys, when I say where's a 45, 45, 90 really come from, you're just telling me it's what?
Half a square.
Half a square. Okay, so let's just do this real quickly. I want to make kind of a T-chart right here. Cut this in maybe the two sides like this. I want to talk about what this theorem says right here. All right? It says in a 45, 45, 90-degree triangle, the hypotenuse is, this is a big important piece right here. This is the part. It says it is the square root of what? 2 times as long as what? Each leg. Okay, now kids, I've got a concept we've got to make sure we're good with, all right? This is something that should have been covered at the end of last year for you guys. I'm not sure it was, given where we were, so I just want to quick review this. You might want to write this down. Is there a blank side on the very back of your notes?
Yeah.
You might want to write this down, okay? Quick review here. Call this review Rationalizing. What's that bottom number in a fraction called?
Denominator.
Oh, good, denominator. Okay, kids, sometimes in math, you end up with answers where there's like a square root left in the bottom, or the denominator. And rules of mathematics would say we don't want an irrational value in the denominator, so that's why they call us rationalizing a denominator. So here's an example. Suppose I had something like, I don't know, 16, I don't want to use, yeah, what the heck. We'll go 16 over the square root of 3 as an answer, okay? Now kids, when we leave answers like that, we say we can't leave it like that because we have an irrational value in the bottom. We have a square root in the bottom. And the way that you get around that is this. If you multiply something by 1, are you really changing it? If I say 45 and say, let's times it by 1, what do we have now? Oh, same thing, right? Okay. What we choose to do to rationalize this right here is this. Anybody know?
Multiply the square.
Yep, you multiply both the top and the bottom by that same square root that's in the bottom. Now, if the square root's not in the bottom, do I really have to do anything? The answer to that is no. But here's what ends up happening, kids. I have no idea what 16 times the square root of 3 is here. I just leave it as 16 times the square root of 3 up top. But on the bottom, watch what happens here. First of all, what's 3 times 3 going to make down here in the bottom? So this is like the square root of what? And the square root of 9, simply put, is what value? 3. Okay? Now I want to make sure you understand this. I took the square root of 3 times the square root of 3 and got what value? If I took the square root of 5 times the square root of 5, what would I get? If I took the square root of 6 times the square root of 6, what would I get? If I took the square root of 8 times the square root of 8, what would I get? If I took the square root of A times the square root of A, what would I get? Does that make sense? There's some sort of science here alive right now. Okay. So, now the way it's written, this and this is the exact same thing because we really multiplied by what value? Root 3 over root 3, one thing over the same thing, is really multiplying by what? 1, okay? Do you have a radical sign in the denominator anymore?
No.
You do not, okay? You don't, and that's what's important right there, okay? So let's move on to this over here. Why is that important? Well, here's the reason. Sometimes when you're dealing with 45, 45, 90 triangles, root 2 is not going to end up in the numerator. It's actually going to end up where? In the denominator at times. Now, I'm going to make this as simple as I can for you. I want you to just sketch out 2 45, 45, 90 triangles. Oh, I don't need that. Let's do this. That'll work. try to sketch out two 45, 45, 90 triangles as best you can. That's pretty good, isn't it? Put one over here.
Oh, I'm in my small.
That's okay, as long as, I'm going to fix mine here quickly so they look a little better. They don't look quite right to me. Guys, let me ask you a question. What I've drawn up here, does it look like the left side and the bottoms are about the same length?
Yeah.
Do this for me. Okay? Call this here, call this a 6, and call this a 6. Right there. And then what I want you to do is to call this maybe, come on, Parson, thing.
8.
Let's go 20 with it. Actually, 8 is good. 8 is good. Okay, and then on the one over here, I want you to put a tick mark here and a tick mark here. What's that indicating again? Okay. Kids, I'm going to come back over here, and I want to talk about this first one right here. First of all, the triangle that has the two 6s there for legs. Okay, and I should probably put a right angle symbol down here so that I'm telling you that this is what kind of a triangle. Okay. If I did this right here, watch what I do. Do we know what this length right over here is, kids? No clue. Now watch this right here. What theorem could we use to find that length? Exactly. Now, Ellie, is this a hypotenuse I'm looking for, or is this a leg I'm looking for? So I could go and call this really C, couldn't I, if I wanted to? So are you telling me right there on that one, Ellie, that I could go 6 squared plus 6 squared equals C squared? Is that right?
Yes.
What is 6 squared, kids? Okay, now this is an interesting problem, and I want to show you why it's interesting. But do you guys agree that 36 and 36 add up to 72? Now you guys have been programmed in the past to say, at this point, you would do what with 72 to find C? You would square root this. Okay. Now, we haven't talked much about simplifying square roots. Don't really need to write this down. Maybe if you wanted to at the top of the vocab part, write these numbers down. Anybody got to guess what the next number is?
Okay.
Anybody got next?
36. 49.
What are these numbers? Yeah. Oh, what's after that?
81.
Oh, 100. Ooh, now I'm stumped.
121.
121?
144.
That's probably good enough right there. What would be the next one? Anyone know?
I was wrong.
What was it, 13, 196?
Close. 169 to 13. Okay, here's the concept that comes up with 45, 45, 90. First of all, read the theorem again for me. It says in a 45, 45, 90 triangle, the what? The hypotenuse is how many times bigger? Square root of 2 times long as what? This is saying, okay, what is each leg in this, kids? So the hypotenuse would be 6 times what value? Square root of 2 to be this length. They're saying that this hypotenuse is 6 times the square root of 2 times longer. Okay? Now, if I punch in the square root of 72, does my calculator kick out 6 root 2? Or does it kick out some decimal for us? Okay, here's the deal. Why did I put these numbers up here? Well, here's the reason. Okay? We would like the square root of 72, but part of your assignment back on 9.1 is to give an exact value, saying, meaning leave it as a square root. And what we try to do is we try to break 72 down as a product of the largest perfect square possible. So you start with high numbers and work yourself down. Guys, where would 72 fall in this list right here? Between what two numbers?
64.
Okay, so let's start asking ourselves questions. Will 64 divide into 72 evenly?
Yeah. No.
Okay, will 49 divide into 72 evenly? No. How about 36? Will 36 go into 72 evenly? Okay, if you weren't sure you'd have a calculator, you would type in 72 divided by what? 36. What is 72 divided 36? 2. Okay? This 72, this root 72 is like the square root of 36 times the square root of 2. But guys, what is the square root of 36? So they're saying C would equal this perfect square that we took out, 6 times what, kids? Isn't that what that theorem says right there? If this was a 9 right here, so if the 6 was a 9, what would the hypotenuse have been then? 9 square root of 2. But this only works in what kind of triangles? All right, so here's what I'm going to tell you. I'm going to make a note up here. You probably want to do this. If I'm going from a leg to a hypotenuse, I'll abbreviate HYP. You're going to times by root 2. Okay? And I should probably write the word times in there. You probably don't want the x root 2 in there. You probably want to say times by root 2. Okay, so what I'm saying here is this. We knew the two legs in this. The legs were 6 and 6. To find the hypotenuse, you take a leg times what value? I'm multiplying because is the hypotenuse longer or shorter than the leg? But what if I give you the hypotenuse first and have to work back to a shorter leg? Then you would do what? Divide by root 2. So let me write this down. What did I give you right here, kids? And is the 8 the hypotenuse or the leg?
Hypotenuse.
Oh boy, so here's how this works. If you know the hypotenuse, and you have to find the leg, instead of multiplying by root 2, what do you think you're going to do? Divide by what? Oh boy. Okay. Let's do some work up here. What is the hypotenuse in that 45, 45, 90 over the kids? It's 8.
Oh.
And I have the hypotenuse. And I'm working back to a leg. So I'm going to multiply by root 2 or divide by root 2? Okay, so do you guys agree that the legs in that one over there would be 8 divided by root 2? Just like this?
No.
Oh no. But what's the problem there?
The root's in the
There's a root in the... Dang it. Okay, no problem. We know how to handle this. So what are we going to do to both sides? We're going to rationalize it by multiplying a form of 1. So 1 over what? Root 2 over? Okay, friends, talk to me. What's the top simply going to become? 8 root 2. This would be the square root of 4 when I put them together, right? The square root of 4, you know, is 2. All agree? Now, kids, I could go one step further right here. Look at the parts that under are the root. How about 8 over 2? What would that simplify to? You see that then? So this would be 4 times what then for a length? 4 times root 2 is what you would have here. This would be a 4 root 2. And we'll look at some more examples here. But kids, this is the big idea. If you have what type of a triangle? 45, 45, 90. In other words, half of a what? Squared. If you know the legs and want to find the hypotenuse, take the leg times what value? Basically, you're going from short to long times. If you know the hypotenuse and working back with shorter legs, instead of multiplying by root 2, you would divide root 2 there. Okay? Let's try example 1 here. Let's see if we can figure this out. Show of hands on A, please. Am I going to first of all multiply or divide to find x there? And first of all, why do I know that this is a 45, 45, 90 triangle?
Two of the same length.
Same side legs. Okay. What's x simply going to equal here then? 22 root 2. Kids, any roots in the denominator? Is that a good thing or a bad thing? That's a good thing. We're done, right? I really like part B, the way they set this up. Guys, are we going to multiply by root 2 or divide by root 2 to find these two equal legs? We're going from the longest side to Okay, so this would be 10 root 2 divided by what? Now, guys, sometimes this will happen, and this is pretty gnarly. What are the root 2's going to do to each other if one's on top of one? So what are you going to have for both sides? Cool, huh? Now, I wish that every triangle we dealt with was 45, 45, 90, but I think up there in the notes it said there was also another one. Is there? 30, 60, 90. Okay, and my question to you then would be, before we move to 30, 60, 90, how many are like, okay, I think I've got this 45, 45, 90. Let me show you. How many are thinking? You're either multiplying by root 2 or doing what? Okay, so if you start with legs, get longer times. As the hypotenuse gets shorter, divide. You can handle that part, right? Okay. All right. Well, let's move to the second part of this. The second part of this here starts talking about what types of triangles?
30, 60.
30, 60, 90. Okay. Well, all right. There's some rules, just like 45, 45, 90s on this, and I'm going to show you why they work the way they do. But guys, a 30, 60, 90 triangle, this is where it comes from. Okay, if I had a triangle that looked like this, I'll do the best I can. What kind of triangles that appear to be? Equilateral. Put a line here, here, and here. That indicates that all three sides are the same. It's an equilateral triangle, kids. If that's an equilateral triangle, first of all, somebody remind me how many degrees are inside the interior of a triangle?
180.
180. That's smoking hot. Okay. Now, the yeah. Yep. If the sides are all the same, what's that mean about all the angles inside of this thing? So what's 180 divided evenly by 3? Which means all interior angles of an equilateral triangle must be what? That's 60. That's 60. That is 60. Okay? Anybody want to take a guess where a 30, 60, 90 is formed? Or how we use an equilateral triangle to form a 30, 60, 90 triangle? It's half of it. Talk to me about where's your half? What are you doing? So are you talking vertically here?
Yeah, vertically, yeah.
If I would draw an altitude in here, and altitude is what we call this right here. If I would draw a line right in here, kids, from the very top of my triangle straight down, I missed. Does that look pretty good? Is that okay? Come on, one more. What happened to this 60-degree angle right here, kids? Cut it in half to make what? This angle down here is still what? What about this over here? Now I want to show you something, kids. In this 30, 60, 90 triangle, we have what's called a short leg, a long leg, and a hypotenuse. Okay? If I would have told you that maybe this side over here was 10, you said that this altitude cuts everything in what? Makes this angle 30. If this is 10 up here, then this short leg would have to be half of 10, because this was 10 totally down here, wasn't it? What would that distance have to be?
5.
5.
How do you spell equilateral?
Okay, it's EQUILATERAL. Okay? So a 30, 60, 90 triangle is half of what type of a triangle? Okay, and we'll write that down here in a second. But here's what this is saying. Now, kids, I can go through Pythagorean Theorem and show you this again, or we can take the rule like we did on the 45, 45, 90 triangle and run with it.
Yeah.
Check this out. It says in a 30, 60, 90 triangle, the hypotenuse is what? Twice as long as the short leg. So the hypotenuse, what is the hypotenuse in this right half here, kids? What did I call that? 10. Is always twice the short leg. This would be 5. And the longer leg is what?
Root
3 times as long as the what? So if the short leg down here is what, kids? 5, that means that the longer leg would have to be 5 times what? Root 3. That's what that formula says there. Okay? Now again, if I wasn't sure about that, I'll write this down up here. You don't have to do this, but check this out, kids. Is this height that we didn't know right here a leg or a hypotenuse, kids? I'm going to call that like an A. If I went A squared plus, what's the shorter leg in that drawing so far? What was the hypotenuse, 10? Okay, help me with my north of Highway 3 math skills. This is A squared plus 10 squared is, you're with me, subtract 25, I've got A squared equal to what?
75.
Is 75 a perfect square? Where would 75 fall? Okay, 64 going to 75? You know, it will, but just not wholly or evenly, right? 49 going to 75? 36 going to. How many times will 25 go into 75, kids? So this is like saying, this is like A would equal the square root of 25 times the square root of 3, because the perfect square that comes out of 75 is what? How many times? You guys help me out. What's the square root of 25? So that means that A would be 5 times what? Isn't that what that theorem told us right here? Okay, let me draw one up here. Okay. Now the thing I want you to understand is this. I'm going to divide this up this way. Okay, and I'm going to draw two 30, 60, 90 triangles in here like this. Draw one that kind of looks like this, longer on the bottom. I'll put some right angle symbols in here. Okay. Guys, the two angles that are up there, which one's the 30-degree angle and which one's the 60-degree angle? So right here, it's a bigger angle, right? And what's this down here, kiddos? All right, talk to me, friends. Where is the shortest side at in this thing? It's on the left, okay? Listen to what I say, this is important. The shortest side is always opposite the smallest angle. Or in this case, what's the smallest angle in my triangle? So across from 30 degrees or opposite of 30 degrees will always be which side? Okay, I'm going to try something here. I'm going to put a value in. Okay, you ready for this? I'm going to put a 9 right here. Okay, what length did I just give you? Did I give you the short leg, the long leg, or the hypotenuse? Okay, talk to me, friends. How do you find the hypotenuse in this? What's the rule?
Half equal plus something root 3.
Yep, so the hypotenuse is what? Twice the shorter leg. Okay, so down here, is it okay if I write down the hypotenuse? Has to equal the short leg times what? Okay, the hypotenuse in a 30, 60, 90 degree triangle is going to equal short leg times 2. Well, what the heck is the short leg, kids?
9.
So what's that make the hypotenuse up here? Okay. Then it says the longer leg is what?
Root 3 times is longer for shorter.
Okay, so the long leg, I'll write down LL. That's going to equal the short leg times what? And I'll ask some questions here in a second, but isn't this my long leg right here, kids? Well, what's the short leg length? So to get the long leg length, we're going to take that short leg length of times. Okay. So I'm going to put some formulas in here like this. This can be a little tricky. If I put down here, this is A. That's the short leg, isn't it, kids?
Yeah.
Then the long leg would be A times what? And then help me out. If A is the short leg, what's the hypotenuse? A times what? Which would be? Careful. That would be A times A. We want A times. Yep, but you would have it right there. So let's see if we can't make this work. Here's your triangle, kids. I want you to see if you can come up with the length for y and x for me. So 30, 60, 90. By the way, how do I know if this is 30 degrees down here, given what's here and here?
So this is 90 plus 60 is
Okay, and 150 from a total of B. Very good. Take about 31 seconds and find y and x and check with someone around you. Make sure you agree. Once you have x and y figured out, let's check with someone around you and see if you agree. Let me ask a question here first. What length did they give you? They gave you the hypotenuse, right? So, which variable represents my short leg here?
Y.
In the diagram, y would, right? How's that diagram out to work, kids? If this is a y value right here, what's 30? What's this got to be? 15, right? It's half of the hypotenuse, okay? Well, if the short leg is 15, what's that make the long leg?
15.
Yep, 15. I have a question, kids. Instead of doing something like this, what if I gave you the, well, in fact, I think that this next example does this. If I gave you the long leg and wanted to work back to the short leg, I wouldn't times by root 3. I would actually work backwards to divide by root 3 here, okay? And that's kind of what's going on right here in this next example. This is a great example. It says a warning sticker is shaped like a, what kind of triangle? With side lengths of what? Okay, so this would be 4. This would be 4. This would be 4, right? What are we trying to find? So the interior here, right? Estimate the area of the sticker by finding the area of the equilateral triangle to the nearest what? Oh. Well, what's the formula for the area of a triangle? Kid?
Half of base times height.
Okay. Do we know our base length down here, kids?
4.
All agree it's 4?
4.
Yep, so my area is going to equal half. Ooh. I don't see a height listed here. Okay, but this is an equilateral triangle, right? And by splitting this in half right here, by splitting this in half, what kind of triangle is that formed in here on the left? Okay, what would the short leg length be then?
2.
So how is the long leg here in the middle related to that?
2 times 3.
Yep, since this is 30, 60, 90, this becomes a height of 2. That'd be that short leg down here, right? Isn't 2 half of the 4 down here?
Yeah.
Be 2 times the square root of. So what am I going to plug in for height over there to continue to find your area? Times 2 root 3. All right, I need some help, minions. Half of 4. 2 times this 2 right here is what? 4 times what? Okay, now, if you left your answer in radical form like this, 4 times the square root of 3 square units, that's cool. But I think they said, go ahead and give me an estimate and round to nearest 10. So in your calculator, I need someone to type in square root of 3, and then take that answer times what value? 4. Well, that's about 1.7 and 4, 3.4, 6. Pretty close to 7.
Cody got it.
Cody, you punching for me, buddy? Square root of 3 times 4 for me. You square root of 3 first, and then times that by 4. I'll take that times 4. 6.93. Well, we said round to the nearest tenth of an inch. There should be nearest tenth of a square inch. So about 6.9, is that right, Cody?
Yeah.
Okay. We get about 6.9 square inches there. Okay, 2 types of triangles today. What's one of them?
Isosceles.
What?
They are isosceles. There's one of them.
Right isosceles.
45, 45, 90.
36.
Okay. Let me just peek and see what's on the next page here quickly. Quick question for you.
That's definitely
If you think of this in terms of either multiplying by a certain root or dividing by a certain root, if you think of it in terms of am I starting with the long side and working backwards to the short side, or starting with the short side and working up to the long side, how long do you think that one? Think about what you're starting with here, okay? Let me see what I have here on the last page. I think you'd be easily finding this. I think we'll be okay here tomorrow when we pick this up first thing, okay? Kids, I sent out an online page for this here. It won't be going until Thursday at midnight, but you may want to get in there and start looking at that. Tomorrow you'll have some time to work on some things, but it'll be a pretty busy day in here tomorrow, okay? So, if you want to get started on that online page, that'd be a good thing, okay? All right, where is that?